for the end of his studies.
So, I don't know if the mic's on, yeah. So today I'll talk about Dagger. So Dagger, as Arnaud said, is our project. So it's about decompilation to LLVM IR. So decompilation to LLVM IR, we can break it down in several pieces. So the most important piece is semantics. When we say decompilation, we want to express the semantics of the input binary in the target independent LLVM IR. So then I'll also talk about how we plan to implement it. We also have the hand-wavy stuff, like the use cases and tools like static binary translation, things like that. So first, semantics. So as I said, we want to translate from the binary to IR. So here we have an example of x86. So two simple instructions, so an add and a sub. If we look at the equivalent IR, so first we have the operands. So here the operands are explicit in the IR, whereas in x86 the input and the first input and destination operands are implicitly the same. We also have the SSA variables. So we have to recreate several versions of the same register. The IR is typed. In x86 we see that as the type of the register. All in all, we still have our add, so that's the core semantics of the instruction. Now we have the sub. So the sub is more complicated. We have the memory operand. So we see first we have the base offset computation. We have to cast it, once again it's typed, so we have to cast it to a pointer. Then there's the memory operations themselves. So we have to load and then store the result back. So there we have it. So this is basically the end result. From the two x86 instructions, we have the equivalent IR. There's more complicated. There's lots of instructions that have the same semantics. Like for instance, if you take x86 sub, there's dozens of subs. Like for 32, 64, 8 bits, for whether the operand is in memory, in the register, it's an immediate. However, the core semantics are exactly the same. So what we need is a way to define semantics of the... We need a way to define semantics in a way that's generic to all the variants of the same instruction. So for that we introduce mirror code. So we'll see mirror later. For now, let's just focus on how we define semantics. So here we have the semantics of the sub. So just subtract and set the result in another operand. So we have the input operands, VOP1, VOP2. We also need to associate the semantics we wrote with each instruction that has these semantics. If you look at the table gen operands, so here we have the sub32 instruction. What's interesting for us in the out and in operand lists, so here we have the i32 mem operand, so this was the base scale index offset operand. In the table gen, it's defined as the operand class. We also have the gr32, so it's a register class. However, when we first disassemble the binary, so it's the first thing we do, we actually only have MC operands. So each part of the base scale, index, offset, and I think there's one for the selector too. Each one is split in as a different MC operand. So we also have the EAX operand at the end. But we need a way to map these to the here we see to the in operand list operands. So what we do is we define virtual operands. So virtual operands are a way to map. In this case, we have input operands. Like for instance, to map when we encounter a register class, for instance the gr32 in the sub x86 instruction, the semantics of the register class operand is like we get the register value. If we have the table gen operand class, we look for the operand mapping, so we'll see exactly how we define the operand mapping. For output operands, it's basically the same. For operands, there's the operand mapping. register classes, we put the result back in the register. So here we have the example of the operand mapping for a register. So we define two instructions, two nodes in the table gen. So there's the get node, which means get the nth register. Like here in this case, it's MC up 0 will be replaced by the value of the MC operand, let's say 43 for EAX. This means like get the 43rd register. There's also put, like for output operands. So we put the result. Result is a special node in the table gen. Result, we put the result back in the MC up 0 register. So here we say MC up 0 because at this stage we define the operands at the MC level. So here we say like it's the 0th MC operand starting at where we're at. So this is relative to the current operand. We also have immediates. So immediates, another node we define is move. Like it's just the value of the expression is the value of the MC up 0 node. For output operands, well, it doesn't mean anything. There's a more complicated thing like custom operands. So custom operands, in this case we have the base index scale offset calculation. Here we do it by hand because it's somewhat clear for non-LLVM initiates. We could also do something like get element pointer, but it would be less clear for outsiders. So here we do the base scale index offset calculation. So we see that this is the first MC operand, and then we use the next in the relative to the start of this whole operand. So it was the I32 mem in the sub x86 instruction. In this case, we just use the semantics fragment. So this was a semantics fragment. We just use the semantics fragment we define. So we load at this address for input operands. We store the result at this address for output operands. So all this is quite easy. Now when we encounter the exact sub instruction, what do we do? So we expand each virtual operand to the equivalent semantics, the semantics fragment. So for instance, in this case it's sub32 MR, I think it's quite small. Sub32 MR, so the first operand is a memory operand. So we do the base scale index offset computation. We load from there. We also have the get because it's MR, so the next operand is register. So we do get. Here you notice that it's 5 because it's the 6th operand in the MC level. So here we have another simple example. So we have sub32 RI. So RI, well, the first operand is a register, the second is an immediate. So at this stage, all we have, so we're still at the table gen stage. We're writing our semantics in the table gen. At this stage, what we have is we expand this DAG. We expand it into, so what I said, the virtual operands, we expand them into the node. We have a tree of the semantics that correspond to this instruction. So in this case, we see that our end result, what brings us closer to the LLVM IR level, first we need type information. It's not really type information, we only need sizes. So at this stage we do type inference based on what we declared at the table gen level for the LLVM backend. We use the type information, we do type inference, so here we see that both of these are 32-bit operands. So here we use the 32-bit variants. I'll talk about this later. So at this stage we also do, we flatten the DAG. We create a list of instruction. We use SSA variables for each instruction. So at this stage what we have brings us closer to LLVM IR. It's just a transformation from the untyped expression tree. So this we call mirror code. Basically mirror code is the intermediate step between the binary and the IR. Mirror code, it's basically the same as IR. We have a few differences. For instance, target registers. In this case, I talked about the get and put nodes. Get and put are a way to make available the target registers at the IR level. At the IR level, all we have is SSA values. So what we do is we have the get instruction, so this means gets the 4th register to the TD0 value, put the other way. We also have another specific to the mirror code, so it's the advanced instruction. So here we see we have an add that's located at the address 9. We just do advance at 9 to set the start pointer, the start offset. Then we also see that the add has 6 bytes, so we advance plus 6. So this enables us to handle the program counter easily, so we don't have to do the calculations by hand. At this stage, what we have is quite close to IR. We have most of what we need to create the semantics from the IR level semantics. So there's just a few things more transformation based on the mirror code. So here we have two x86 instructions. First we have a sub, so we sub ECX from EBX. We add 12 to that. So here we have the mirror code. So we subtract, we put it in EBX, goes through EBX. We move 12 to a value, we add both of these, and we put back to the register. So when we see the IR, at the IR level, the starting point is the add. So we focus on the add here. If you look at the operands of the add, so the first operand is EBX2. So EBX2 was defined by the subtraction here. So here the output operand is the TD2 value. It goes through EBX. It goes through TD0 then, and it's found here. So here it's quite easy using just a map from each register to an LLVM IR value. It's quite easy to just map these, the EBX2 value straight from the sub to the add. We also have the move, so the move is even easier. So here this line is replaced by, it's translated to a constant value which gets into the add instruction at the IR level. So there we have it. So that's how we transfer from the x86 to the mirror code and to the IR. So that way we created values from target registers. There's more complicated cases, like for instance branches. In this case we have an address, an add located at address 22. We do a jump to 22 later. Here in the mirror code we see we have the advanced 22, we have the advanced plus 4 because this is 4 bytes. Then we have the jump. So in the IR, this is equivalent to just adding a label to the add. So this is the semantics from the add. Then we just do an unconditional branch to that label. Now this is the easy stuff. There's also indirect branches. So indirect branches has always been a complicated problem in decompilation. So in this case, the most we can do statically at this point, the most we can do is to just, for every address, for every instruction, like here it's at 22, 26, just create a label for each of these. And that way, we can create a jump table. So when you have an indirect branch instruction, you just jump to the jump table, put the right value, and get from the I64 of the integer value, the integer pointer, you can get just the exact LLVM IR level. So we'll see later ways to remove this, because this means for each instruction we have to create a label, because we don't know statically what instructions we will jump at through an indirect branch. So this is really the ugly stuff of static decompilation. We'll see later just what we can do about that. So there's also predicate instructions. So for instance, we have the ARM add GE. So here we add 1 to R5. We add it to R7 if the greater or equal flag is set. So here in the mirror code, we just do the computation in the IR2. We use the select instruction, even though Chandler doesn't like it very much, I said to him. The TD3, we put it in R7. In this case, we select depending on the condition flag. So the condition flag, I didn't talk about condition flags yet. How exactly can we compute condition flags? So in this case, we just have simple instruction, 22, a JNE. So JNE, we jump if the not equal flag is set. It's not really the not equal flag. we have the advance, we have the compare. So here what I didn't tell you, what I didn't show in the previous slides, is that for every instruction that updates the e-flags, so here in x86, so we have the e-flags register. For each instruction that updates the e-flags register, we just compute every condition code that's in the register. So for instance, we have CMP NE, we have CMP GE, things like that. So that way, every time we compute a new value that updates the flags register, for instance in x86 add does that, we just compute all of these. However, at the IR level, when you translate to IR, if the value we defined isn't used, it just gets deleted. So that way, even if we're stupid at the mere level, it's easy. We can get away with it and compute just the right flag when we need it. However, when we need to get really the e-flags in whole, then as we have the dependency on each flag, they all are left in the IR level and form the e-flags register back, for the e-flags value back. So we see that we use the NE flag that we computed right here to just to do the branch, the conditional branch. So here now that we have the IR, what exactly can we do with this? So here, as I said, is the hand wavy stuff. There's lots of things. For instance, binary rewriting. Like we have a binary. It jumps through decompilation. We have the IR. The IR can still be target specific. Like for instance, we can have inline assembly. So at this stage, what we want is to optimize the program using additional optimization, using new features of a specific CPU. We also sometimes we also want to add things like instrumentation to the binary. So the first problem is missing semantics. So missing semantics is things like we can't really express at the IR level. For instance, things like read timestamp counter, x86 instruction. This, as I said, we can just, inline assembly works fine here. There's also the data section with things like alignment, padding, things like that. So we can just map the whole section itself in the output IR. There's also static binary translation. So as I said, static binary translation has lots of problems. There's other things you can't really do statically. For instance, the indirect branches. There's also things like how to discover code. If you do statically, you just have to start from the entry point of the program. But there's things like, well, it's rare, but there are things like in x86, you jump through the middle of an instruction. How can you detect that statically if it goes through an indirect branch? There are lots of things you can't really do statically. So dynamic binary translation is preferred to that. It's not an alternative, but it solves lots of problems. For instance, things like self-altering code. It's a fringe use case, but self-altering code, when the code modifies itself, so it's really used in x86. The usual trick used by valgrind, QEMU, things like that, is to mark the translated pages read execute. That way when someone tries to write to it, it just signals, and then you can retranslate the whole page again. There's also the problems I talked about, code discovery. So code discovery is solved by translating just when we need it. So for instance, in the case of the indirect branch, when we have the indirect branch, we just dynamically we have the value, so we can just create a new basic block starting at the pointed value and retranslate a new basic block starting there. So this way we solve most problems from static binary translation. There's also, so it's a variant of dynamic binary translation, instrumentation, things like valgrind check. We could maybe write that using just an LLVM pass. There's also binary analysis. So for instance, in the security research world, I see lots of use cases where having semantics would really help. For instance, the ROP. ROP is return-oriented programming. So you want to create your payload, so you want to create your executable using just sequences of instructions that end with a branch. So you have to go through the whole binary by hand, just check for the instructions you want that create the desired semantics. So we have a member of our group that did research on that, the Rob Gadget. So it automates some of it, but we're thinking about bringing it higher. So for instance, instead of just looking for certain patterns by hand in the binary, we could just write some mir code or some IR, but IR isn't really fit for that. We can just write some mir code, and after that we match the mir code using constraint solving. We match the mir code in the binary so that we find a sequence of ROP instructions that just make up exactly what we want, the semantics that we want. So there's lots of things like that in the security research world. There's also simulation. So this is more for fun use case. It's not really serious for things like, I don't expect it to run like out of order Superscala x86 in the processors, but for things like video game consoles, like the old CPUs you want to emulate. So there's an easy way, really easy way to do that. You just write your LLVM target. You can also, like, for instruction, you write the semantics of all your instructions, and then using that you can even go further. Like for instance, if there's instructions that you can't really write in the semantics, as you have access to the simulator itself, you just have to write some hooks into the simulator. You have access to all the processor state. You can just write the missing pieces. You can also have a somewhat cycle accurate. It's nowhere near cycle accurate, but you can do an approximation using things like the machine model, the pipeline information in LLVM. Now there's also the huge use case. It's two-source decompilation. So with that we want to output C-source. C-source we need a C backend. So we need to revive the C backend. We need to make it fit for human readable output. The old C backend that was dropped a while ago, it was fit for another compiler. We need it to be readable for a security researcher, for instance. There's also lots of optimizations to be done. I call that IR hiring. It's hiring because when you optimize to compile, you do things that are opposite from what you want to decompile. For instance, inlining. Inlining is like the most useful optimization when you compile. Here you want exactly the opposite. You want to extract pieces of the whole function you just decompiled to recreate the functions you want to read as the researcher that reads the decompiled source code. There's also things like aggregates. At the binary level, there's no such thing as aggregates. You just have a sequence of integers, no, not even integers, just bytes. Sometimes you address them using 8 bytes, things like that. But what you want, when you read the code, what you want is structures, arrays, things like that. So this is, once again, this is the opposite of what you do when you compile. There's lots of optimization to be made here. There's something else. It's like decompiler will never be perfectly accurate. It doesn't mean anything. We can use some help from metadata. For instance, symbols is the easy thing. When you have symbols, you have the address, starting address, and the size of functions, of globals too. You can take it even further. For instance, in C++, if you have the symbols, you just demangle the symbol. You have lots of information on the arguments, on the hierarchy. On C++, there are also things like runtime type information. So there's things like the vtable, things that you can use to hint the decompiler at what exactly it's decompiling. That, yeah, we have a class, we have this pointer, it means this, we have these methods. You can take it even further in Objective-C. Objective-C, you have the whole runtime that needs lots of information on the binary itself. So you need things like the class hierarchy, things like the methods, the variables in an object. So lots of things you can do using metadata that's available in the binary, if you are lucky to have them. So now that we have some idea of what we could do of decompilation, there's lots of things to be done right now. So right now where we're at, we can do translation from simple instructions to mir code. Then we can translate the mir code to IR. So that's where we're at right now. there's things like the selection DAG. Selection DAG is a hot topic right now in LLVM. I'm not sure what exactly will happen with selection DAG patterns. So patterns, you may have noticed that as selection DAG patterns are really close to what we intend to write using semantics. So I'm not sure exactly how we could do that, but I feel like there's a way to unify the semantics and the selection DAG patterns. That way we only have a single infrastructure for all the semantics appearing things in the table gen backends. We also think about removing the mere backend. As you saw, it's really close to IR. We did it because at first we had lots of more differences. So now I'm not sure if it's worth it to just decompile to IR straight. With what we're thinking is using the mere backend, we can add specifics that we can't just use at the IR level. There's also all the analysis and hiring to do. Finally, there's all the tools too. So there you go. Are there any questions? Micro. It's shut down, I think. Yeah.
Is it work? So you talk about a lot of analysis and hiring. So I was wondering, do you have any plans related to loops in the code?
Right now, we didn't really go really deep in the analysis stuff. So we know there's lots of things to do, but loops, I'm not exactly certain what exactly we could do about that. So right now, no, we're not at that stage. So it's further down.
Yes, I asked that because I've seen that these days almost no one writes as a programmer irreducible loops, but in a binary you often do end up with irreducible loops, and in the LLVM framework I don't think there's any possibility currently to analyze those. So yes.
Things to write to.
But,
yeah. That's
okay. I think you haven't mentioned some of the things that matter when you are decompiling C code, like the stack and function calls.
Yeah.
And maybe even the eFlags register, because sometimes programs just tend to read it and make something to it. So because you don't shadow it, you don't propagate the state of the eFlags, there may be problems.
Actually, the eFlags, when we reference the eFlags register in the mirror code, in the input binary, we just recreate the eFlags register as is. So we just recompute each flag, so that way we have the input eFlags register. After that, after a store to the eFlag register, we just recreate each individual flag that will be used in the IR. So that way, modification to the eFlags, that's what you're talking about, right?
What about the push flags instruction?
That's the complicated things. In this case, yeah, push, it's just an assignation to the eFlags register like most other. So in this case, the push will be translated to the mere semantics of like, we store it to the incremented or decremented depending. What we do is, at the mere level, there's the same IR, the same reference to the eFlags register. So it's the same. You just have to recompute each flag and create a eFlags register. And when you store to it, when you load the eFlags register, then you just have to recreate, split it into each individual flag. So I'm not sure what's the problem with the.
Well, maybe we can get to that offline. What's about function calls?
Function calls. That I talked a bit about all the possible analyzes. So yeah, the most useful analysis when you decompile is creating functions. We think about using, as you said, things like the epilogue, prologue. When you manipulate, like when you change the frame pointer, we see that as a hint that you're starting a new stack frame. So there's no easy solution, but we just use things like that. So something else like that is that when you have references to memory that are based on the ESP register, on the stack pointer. You can infer from that it's a variable, a local variable. So there's lots of things like that really specific. As you said, we can talk about that later, but lots of specific stuff to be done there.
Yeah, thank you.
How robust is it?
Excuse me?
How robust is it? Have you tried it on big code base?
Oh no, we're nowhere near that stage. Right now we're just focusing about how to express the semantics in an efficient way on simple sequences of instruction. We're nowhere near the huge programs. We'll see.
Okay, and one more question. What subset of x86 instructions are you focusing? Are you supporting AVX and AVX2 particularly?
Right now we're nowhere near that. Right now, semantics is never-ending thing. Right now we're just focusing on the core instructions. It's just about the design of how to implement the semantics. We're not nowhere near something that's really usable for modern AVX instruction.
Okay, and what about SSE, at least?
No.
No, okay.
Nothing.
So just core x86 instruction without vector stuff. Okay, thank you.
So can I ask a follow-up question? I was wondering how difficult it would be to extend to support those instructions. I mean, your framework is in place, right? So
Parts of it?
So if you build further on that, are there any fundamental problems to also support those instructions?
These things, I'm not sure it's really the difficult stuff. These, you have most that's needed to express things like vector, shuffles, things like that. I'm not sure this is really, won't be really much of a problem. So we're not yet at the vector instructions. We're just focusing on simple. But I don't think this will take really that long. Yeah.
If you got an opcode that modifies the parity flag, how do you calculate the parity flag?
The parity flag is a special problem. In this case, yeah. This is really a common case.
Okay, because I did almost the same, but I'm using it. I'm using a small stub on the LLVM IR, which calculates the opcode. I mean, it blows the code a little bit, but it does exactly the same calculation. Would this be something that you could also use, or?
Yeah, I think it would. I'm really interested in. Yeah.
Yeah, we could talk afterwards.
Yeah.
Okay.
Which approach do you use to support stuff like software breakpoints or other things like that? Like calls to operating system?
This is, when you mean stack breakpoints,
Software
breakpoints, yeah, sorry. When you mean software breakpoints, what exactly do you think about the decompilation? I don't see...
well, like if you decompile operating system software, like if you want to use that, for example, to do full emulator, for example, for dynamic binary translator, I don't know.
Can you elaborate on that? Not sure.
Well, I mean, there are some instructions that are protected, right? I mean, only the operating system can use them.
Yeah.
That specific semantic. I mean, I guess how you deal with those, like int, for example.
This is, as I talked about earlier, like there's lots of instructions like these that you can't really express in semantics. So for these, depends on the specific tool. So in the binary rewriter, as I said, you can just inline assembly. But for other cases,
depending on what you want to, how you want to use it, you deal with them in a specific way.
Yeah.
Okay.
Because at the IR level, it doesn't mean anything. Like you could maybe do just write a function that you provide that could maybe do something that's close to it, but doesn't mean much. So yeah, this is the problem with these type.
Okay. Okay, thank you.
We have a question here.
Is it different to decompile some code that was generated by LLVM compared to decompiling some code that was generated by another compiler? I mean, it's easier to make a round trip with the same kind of intermediate language, or is it just the same?
No, at this stage doesn't change much. Really, the huge difference, if you had any difference, would be like things like that he talked about. Instructions that are really specific to the architecture, that do input, output, interruption, things like that. But depending on the compiler, it's more of the same. Like you just have this, the patterns themselves will be different, but using at the output IR, it looks the same. So there's not much of a difference at this level.
Even to reverse engineer optimization?
Well, I'm not sure what you mean.
I'm not sure myself, but I guess from the basic source code, LLVM performs optimizations, and sometimes if you want to go back to source code, you will have to revert those optimizations in a way, and to be able to correctly revert the optimizations, then you need to know what were the optimizations. Yeah. So that's
it's related to something. It's related to something that I didn't explicit, but right now what we think of the two-source decompiler is we don't really want to match the input, the source code that produced the input binary. So we don't really care like to reverse each specific optimization to be closer to the binary, to the input source code. We just want a way to have the binary in a human readable way. So all these cases, like to reverse a specific optimization, we don't really care about that. So I'm not sure if it's really important. Like in a way, if you want to have the really close to the input source code, then yes, you would have to do things specifically to some type of optimization. But for now, we don't really focus on that. We just want the semantics. Questions?
Okay, one last question. Is that a technical question? Wonder if Dagger is an open source project?
It will be.
It will be.
Soon.
The release coming soon?
Yeah, exactly.
You can tell me more about the coming soon?
I think in the next few weeks we should have something up. So yeah, next few weeks, maybe at most for 2 months, something like that. So soon, really soon.
Okay, so that's the end for the questions.
Thanks.
Thank you a lot, Ahmed.